Hello, my name is Shudong, and I am a PhD student of the Compiler Research Group at UNSW Sydney. And I'm going to present our recent work on automatic synthesis of data flow analyzers. So, why do we care about data flow analyzers? So basically, data flow analyzers, or DFA, takes as input programs and output some data flow facts of the program as its name indicated. So DFAs has many applications, including compiler optimization, bug detection, program verification, and so on. However, creating DFAs can be non-trivial because it requires many things such as DFA-related expertise, and you have to be knowledgeable about this area, and you have to handle all the corner cases carefully when designing them. So we think that it is important and necessary to have an automated tool because for those who are not familiar with DFA, such tool can help them build and correct and DFA a lot more quickly. And even for those who are already familiar with DFA, an automated tool can assist them in handling corner cases and make the whole thing less error-prone. Program synthesis is a research area where people aim at finding programs that satisfy users' intent automatically. It has many applications including program suggestion, program repair, or data wrangling. So we naturally wonder if we can synthesize those DFAs automatically. As we've discussed earlier, a DFA takes as input programs and output data flow facts as results. So here, our goal is that we want to synthesize the DFA itself when given an input-output specification, including a program in the form of control flow graph and the data flow facts expected before and after its nodes as output. We can get those info either manually or by code instrumentation. For the synthesized DFA, it includes its flow direction, meet operator, and transfer function. We consider a family of widely used data flow problems known as the GenQ problems. We focus on synthesizing intra-procedural and path-insensitive DFAs. However, our synthesized DFAs can also be deployed in an inter-procedural and path-sensitive setting once they are integrated with an IFDS IDE framework and an SMT solver. To the best of our knowledge, this is the first study on synthesizing general-purpose DFAs by examples. Previously, attempts have been made to synthesize static analysis rules, but predefined client-specific rule templates or relations are required. There are three challenges in synthesizing DFAs. First is how to avoid search space explosion. Existing program synthesis tasks usually handle common data types such as integers and strings, while our DFA synthesis task focuses mainly on program elements such as variables, constants, and expressions. A simple-minded approach that synthesizes a DFA from fully fledged language like C or Java would explode the search space very soon. Second, it should have balanced expressivity. The synthesizer should be simple but expressive enough to generate a variety of DFAs efficiently. And finally is readability and maintainability. A DFA synthesizer should generate simple DFAs that are both readable and maintainable. So we should not only care about whether the synthesized DFAs are correct, but also whether they are brief enough to be understood by us human beings. To address the challenges in last slide, we propose DFASy, a framework for the automatic synthesis of DFAs. Given a CFG and the expected data flow facts for its nodes, DFASy iteratively generates and validates DFA candidates and outputs the simplest satisfying DFA. Specifically, DFASy aims at finding three components for a DFA that satisfies the specification. It's flow direction, meet operator, and transfer function. So to generate a transfer function, we use a domain-specific language, or DSL, that supports a set of common data flow fact extraction operations, set operations, and logic operations. To accelerate the search, we propose two pruning techniques. The first one is abstraction-guided pruning. It first evaluates partially instantiated DFA candidates from their abstract semantics and then removes unsatisfiable candidates as early as possible. And the second one is brevity-guided pruning. It evaluates the brevity of each DFA candidate with a cost function and keeps only the simplest among these semantically equivalent DFA candidates. Here is an example synthesizing a classic DFA known as reaching definitions. It statically determines the definitions that may reach a given statement. So the left-hand side is the input control flow graph, and the right-hand side gives the expected data flow facts for each node as an output, expressed in terms of the sets of reaching statements before and after the node. Now, the question mark stands for DFA that we want to synthesize. So what does the synthesized analyzer look like? Let's take a look. The synthesized DFA for reaching definition looks like this. It has three components: is flow direction, meet operator, and transfer function. Among them, the transfer function is the most interesting part. Here we see that we need some very expressive DSL to support such complicated operations. From here we can see that it supports data flow fact extractions. Here we use def info. Sometimes we might use use info, and we also have to support set operations. Here we use set difference and set union. Yeah, and logic operations as well. Here we use logical and, and sometimes maybe you need logical or logical negation. This slide shows the complete definition of the DSL for synthesizing transfer functions. For example, here transfer function theta takes a node n and a value set s as input and operate on s in terms of a set expression represented as an uppercase s. So due to the 15 minutes time constraint, we won't elaborate on it here. We have detailed description of the syntax and the semantics of the DSL in our paper. Anyone who's interested in it can refer the paper for technical details. To avoid search space explosion, our first technique is called abstraction-guided search space pruning. It works by dropping partially instantiated DFA candidates from further consideration. if their fully instantiated DFAs will never satisfy the given specification. This is done by checking all the CFG nodes individually. If an over-approximation of their data flow facts based on abstract semantics may potentially yield the expected data flow facts. And the second technique is brevity-guided search space pruning. It works with a cost function. The cost function is a kind of brevity evaluation for DFA candidates. For semantically equivalent DFAs, it helps us to keep only the simplest solution at last. It works by evaluating the lower bound of the brevity of partially instantiated DFA candidates and accelerating the search with branch and cut. The DFASy uses a worklist algorithm, starting with an uninstantiated DFA in the worklist. It runs a loop to process each DFA candidate in the worklist in turn. If we see any candidates that satisfies any pruning rule we mentioned earlier, it simply got pruned. And when we see a fully instantiated DFA, we can validate it and update the best DFA we see so far accordingly. So the left-hand side shows a simplified derivation tree of the transfer function of the example reaching definition, and the right-hand side is essentially the same thing as the derivation tree, but in a more human-readable fashion. We have implemented DFASy and the DSL for specifying transfer functions in Java. We use Suit to construct a CFG in its built-in Jimpo IR and run the iterative algorithm on the CFG for validation purposes. DFASy is multi-threaded, with each thread handling a combination of two flow directions, two meet operators, and two transfer function templates, making its maximum number of threads to be 8. And the experiments are carried out on a desktop with 8 gigs of memory, and the time budget for solving each problem is kept at 1 hour. And the dataset consists of 14 problems. 7 of them are classic DFA problems. The other 7 custom ones are variation of those classic ones. We first create Oracle DFAs for them manually, then we create the CFG. The CFG nodes is described in the Java-like language based on a number of representative CFGs given in standard text and real code by adding nodes if necessary to cover corner cases. Lastly, we run the Oracle DFA over them to get the full specification. In our evaluation, DFASy has successfully found the simplest DFA solution for each DFA problem in 21.8 seconds on average. And to demonstrate the effectiveness of the 2 pruning techniques we proposed, we conducted 3 experiments with at least one of the pruning techniques missing as comparison. We can see that from the graph, the one without any pruning techniques cannot solve any problem. The one with only abstraction-based pruning has found a solution for 9 out of 14 problems, but it failed to find any simplest solution. The one with brevity-guided pruning can find solution for every problem, and it also found 12 out of 14 simplest solutions, but we can see that it is very slow. On average, it takes more than 400 seconds for each problem. That is significantly more than 21 seconds. So we can conclude that those 2 pruning techniques are very crucial for the effectiveness of DFASy. Finally, we've open sourced our tool DFASy, and it is now publicly available. You can scan the QR code on the screen to get access to the paper, the artifact, and the source code. Thank you.